Today we are going to talk about power factor improvement for roll-to-roll vacuum coating systems by using SCR power controllers in voltage sequence control. First off in our agenda, we will briefly touch on the subject, what is an SCR power controller, its mode of operation typically found in this type of application, the meaning of power factor, followed by the introduction of an energy-efficient operating mode, the VSC mode. What is an SCR power controller? SCR stands for Silicon Controlled Rectifier and is the heart of our SCR power controller. Basically, it consists of two thyristors switched in parallel, where one thyristor is connected the opposite way. This is done to allow one thyristor to control the positive half wave of our sine wave and the other to control the negative half wave. SCR power controller are typically used in applications where heating, melting, and bending is required. It can control either the voltage, current, or power applied to a heating element. The SCR power controller is a very precise and efficient method of controlling electric heat. In the diagram to the left of the screen, you can see what a typical application looks like. The bottom left quadrant represents the SCR power controller. It controls the power direct of the transformer applied to the heating elements in our top left quadrant. The temperature measured at the heating elements is typically measured by a thermocouple or pyrometer and provides a feedback to the customer's control loop. This could be a PLC or temperature controller. The PLC or temperature controller compares this value with the target temperature and adjusts the set point to the SCR power controller either up or down, telling it to apply more or less power to the heating elements. This set point can be analog or digital, utilizing bus communication. One of the most common operating modes, phase angle firing, is often utilized for loads with a small thermal inertia. These loads require a high control dynamic. Phase angle firing takes a certain alpha and cuts the sine wave at the angle to allow a certain amount of power to the load. It can be visualized by picturing a dimmer switch and a light bulb. A larger alpha requires a less brighter lamp as opposed to a small alpha. The biggest drawback of this operating mode is the harmonics it creates. This drawback leads us to our next topic, the power factor. Power factor is a way to describe how efficient an electrical system is. It can be defined as the ratio between the real power, kW, and apparent power, kVA. As harmonics are introduced into our electrical system, there is an increase in the reactive power, which in turn lessens our efficiency. This decrease in efficiency is oftentimes penalized by the energy providers. These penalties can be avoided or reduced by utilizing voltage sequence control, short VSC. Here are two simplified diagrams to illustrate the difference between the phase angle firing and VSC. Our standard phase angle firing circuit on the left has the SCR connected to a transformer with a load on the secondary side. Our VSC circuit is a two-stage VSC as the transformer has two tappings on the primary side, each controlled by one SCR. Here we see the difference between phase angle firing and VSC in operation. Whereas in phase angle firing at a given set point, the voltage delta can be very large. The full peak VSC only has a fraction of the delta due to the utilization of the tappings. The effective output voltage between the two is essentially the same. This is a captured screen of an analyzer that measured the total harmonic distortion between the two operating modes. For phase angle firing, we had a total harmonic distortion at around 44%, whereas in voltage sequence control, we were only at 23%. In general, we can assume that at 60% output power, VSC will improve the power factor from around 0.78 up to 0.92. This is seen in the top left graph. The graph on the right side shows that VSC reduces the total harmonic distortion by around 25%. In this slide, it shows the difference between a 2 and a 3-stage VSC. Depending on the operating range and the power factor requirements, a 3-stage VSC may be beneficial. A downside would be the initial and additional cost of another SCR. Hence, a 2-stage VSC is often viewed as the more cost-effective solution. With a 2-stage VSC, we can see that typically a modulation around 53% brings us into the range of a power factor above 0.9. As for the 3-stage VSC, a modulation of already 34% puts us into this range. Here's an illustration of a 3-stage VSC with 3 equal taps in comparison to phase angle firing, similar to what we have seen a couple of slides earlier. And this is a comparison between a 3 and a 2-stage VSC and phase angle firing. This graph displays the difference between VSC and phase angle firing, short VAR, with an inductive load. We can see that up to 80% output power, the VSC is always superior in power factor. Last but not least, here is an example of VSC in an industrial application. While the secondary current at our load is equal at 5000 amps, we see that the primary current is lower in the energy efficient circuit. The energy efficient circuit is 0.1 better in power factor overall. And here's a screen of the analyzer showing an improvement from 0.77 up to 0.93 at this stage of the modulation. In this sample calculation, we assume that the reactive power cost per 100 kW per year and 100% switched on is roughly 1 cent per kVA reactive hours. Our cosinus phi improved from 0.77 to 0.93. This leads to an annual saving of roughly 2,900 euros, which is about $3,190 depending on the exchange rate, resulting in an amortization of the VSC system in about half a year. In conclusion, the advantages of a VSC outweigh the disadvantages. On the pro side of the VSC system, we have maintained the highest level of control dynamics with lowered harmonics and low levels of reactive power, reducing overall operating cost. On the negative side is the larger footprint, as 1 SCR is needed per stage of VSC. Another drawback is also the initially higher cost of the VSC system, which shown in the previous slide is roughly amortized in about 6 months. Thank you.